In the first episode, we said physics is a way of reading the universe, and the first thing we need to read is measurement. So let's start with a simple problem. If I tell you someone's height is 1.75, do you know how tall they are? Not yet. Is that meters, feet, something else? You see, a number without a unit is incomplete. A physical quantity is any property we can measure. Distance, time, mass, temperature, speed, and many more. Every measurement combines a numerical value with a unit. We can write that idea as quantity equals number multiplied by unit. The number tells us how much. The unit tells us what that amount means. For our study of motion, our first foundation is distance, a measure of space in one dimension. Length, width, and height are all distance measurements. The SI unit is the meter, written as m, but the meter is not always the most convenient choice. A coin might be 19 millimeters wide, a room might be 4 meters long, and two cities might be 80 kilometers apart. That coin could also be called 0.000019 kilometers wide. And yes, it is correct, but it sounds like the coin is applying for a job at NASA. So keep in mind, good measurement is not only correct, it should always fit the scale. Different units can describe the same distance, so we sometimes convert between them. Think of 23 meters. Because 1 meter is about 3.28 feet, multiply 23 meters by 3.28 feet per meter. The meter units cancel, leaving 75.44 feet. The value changes because the unit changed, but the actual distance did not. Some quantities are built from other quantities. Area measures the size of a surface. For a rectangle, area equals length times width. A equals L times W. Multiply meters by meters and you get square meters, written as m squared. Volume measures the three-dimensional space an object occupies. For a rectangular box, V equals L times W times H, producing cubic meters, written as m cubed. These are derived quantities because their units come from more basic measurements. Our next foundation is time, the duration of an event. Its SI unit is the second, written as S. But how does a clock know a second has passed? It counts a process that repeats regularly. Old clocks used swinging pendulums. Quartz watches use regular vibrations in a crystal. Even modern timekeeping depends on something repeating in a predictable way. One complete repetition is called a cycle. The time required for one full cycle is the period, written with a capital T. If a pendulum takes 2 seconds to swing away and return to its starting position, its period is 2 seconds. It's like period ask itself, how long does one cycle take? We can describe the same motion another way. Frequency, written as F, is the number of cycles completed per unit time. Its SI unit is the hertz, written as Hz. 1 hertz means 1 cycle every second. So 1 hertz equals 1 cycle per second, or 1 per second. Period and frequency are opposites. T equals 1 divided by frequency, and frequency equals 1 divided by T. Higher frequency means more cycles each second, and therefore less time for each cycle. Suppose a stopwatch balance wheel completes 10 cycles in 2 seconds. Frequency equals number of cycles divided by time. 10 cycles divided by 2 seconds equals 5 hertz. That means 5 cycles occur every second. The period is 1 divided by the frequency. 1 divided by 5 hertz equals 0.2 seconds. So every individual cycle takes 2/10 of a second. 5 cycles per second, 0.2 second per cycle, 2 descriptions of the same repeating motion. The third foundation for motion is mass, measured in kilograms, written as kg. Mass describes an object's inertia, its resistance to changing motion. Push an empty shopping cart, then push the same cart after loading it. The loaded cart is harder to speed up, slow down, or turn because it has more mass. Mass is not the same as weight. Mass belongs to the object. Weight is the force of gravity acting on it. Your mass stays the same on the moon, even though your weight becomes smaller. So physics begins with quantities that can be measured. Distance describes space. Time describes duration and repeating cycles. Mass describes resistance to changing motion. Units make every number meaningful, and derived quantities let simple measurements build more complex ideas. Now we have distance and time. In the next episode, we combine them to measure how fast something moves. But one missing detail will separate speed from velocity. And that is, well, let's find out.